this topic, it's very specific. And to be honest, it's not on this energy test. There's a question about this on the final. Okay, but it fits into energy, so we're going to talk about it here. And it's less prep we have to do for the final because it does fit with what we're talking about. Now, full disclosure, they told us we're probably going to be using the same final because we all have to give the same final. But I was going to read it. But they haven't sent it to us yet, so I don't know for sure what's on it. But they said we're going to be using the same final, so that's what I'm going with for now until I know otherwise. All right, and we're getting down to it. We've got 14 days left, right? Not counting Thursday, which you guys are seniors are at some job fair interview thing. So 13 days. So we're getting down there. But we'll get there. Today, at the end of the hour, you'll get a short, just one. It's basically exactly what we're talking about, and then we'll talk through it tomorrow on video for you to review. Post it on my YouTube channel. Like and subscribe. Smash that like button. All right. So, anybody out there interested in buying my DeLorean? DeLorean, like from Back to the Future? No? Great condition, low mileage. It's really only driven from time to time. Thank you. Some of you slower ones I can explain. Arnold, should I explain it to you? All right.
Wait, can you go back to that? Great condition, low mileage.
Really only driven. Okay, should I explain it to you, Lars? Or?
Yeah, I get it.
All right. So, we talked about this with forces. An object traveling in a circle has to be made to travel in a circle because according to Newton, objects want to travel at a constant speed in a straight line. So the only thing we can do, the example used with forces is a string. A string can only pull, right? So if I'm spinning something on a string, that means it's being constantly pulled inward, right? Right? So if I'm spinning something on a string, it's going in a circle because I'm constantly pulling on it, right? An object, a car driving around a racetrack, if you had a perfectly circular racetrack, there's a constant inward frictional force, right, making it go in a circle. Nothing wants to go in a circle unless we force it to using centrifugal force, right? We've talked about this. We didn't spend much time on it, but we introduced it. Well, a couple things. We know that all rotating objects have a centripetal acceleration equal to v squared over r. Okay, v being the speed, the linear speed it's traveling, even though it's not linear, tangential speed, right? It's traveling out at the edge, right? And what do we know about force? We know that force equals mass times acceleration. So any guesses what the centripetal force equation is going to look like? M times v squared over r. Nice work, Arnold. Nice work. Okay. All right, so a couple of equations on the board. Rounding out, completing our set. We've got the full box set, collector's edition of equations. Okay.
So those are the ones that are just for
rotational, yep. Just for rotation.
What about the KE rotation?
That would be the kinetic energy of rotation, which is not exactly pertinent to this right now, but
are we getting there, or
sort of?
Did we already get there?
We kind of did, but we don't spend much time on it. We talked about it and don't really use it. In a normal year, we would spend a little more time on it, but the tension would equal the centripetal force. Right? All right. So we good here, right? Now, every spinning object experiences centripetal force, including, if you ever ridden the gravitron, or they're called different names, where you stand there and it starts spinning and then the floor falls away.
Yeah.
Right? Anybody ever ridden one of those?
Yeah.
Did you puke?
No.
They spin really fast. Right? Okay. Now, they're fun. If you like spinning rides, if you get sick on spinning rides, you'll puke. Guaranteed on that. Right? But And when you puke on it, it's a mess because it goes all over, right? But oh, there's so many people questioning their life right now. Yes, on that. Oh yeah. No, but I would guarantee about 2/3 of those people on the ride are going, "What did I do this for?" Because it spins really fast. You know, it's fun. But the point is, it spins really fast, and you can do this. This is a picture from inside one of those bad boys. Okay. Right. And if you ever want to see that you guys are, that people are come on, right? Influencing little kids, right? Yeah. Okay, so spinning out faster and eventually he can stand. Dang juvenile delinquents. All right. All right. So, but this guy, the point we're getting at here is this guy basically feels the same thing that I'm feeling right now. Right? He's standing. He feels what is apparent weight, right? And what always opposes weight? Normal force, right? It's got the same basic. No, they're not normal force and it's not weight, right? But he feels the same way. Does that make sense? Okay. In that spinning object, well, what it is this isn't normal force. This is actually centripetal. That's going to relax be poor choice. This is actually centripetal force, right? Right. And this isn't weight. This is what we would call centrifugal force, right? But it's the opposite force of centripetal force, right? But regardless, this guy feels it. We in agreement there? Okay. And it just so happens if we get the right velocity, we can essentially simulate gravity, simulate weight. Make sense? That's like there's a Star Trek where there's a space station. If if you've ever watched sci-fi movies where they have these big, enormous, circular space stations,
to make gravity.
that they can actually spin those and simulate gravity. It will work, right? You just have to get all that construction material and spin, But the concept works. Okay, for that reason. So if we spin a cylinder with whatever radius you want it to be, if we spin it fast enough, we can simulate gravity, right? That's a force, we can make them equal. Make sense? By adjusting the velocity. Make sense? So this all makes great sense if we're rotating on a flat plane, right? Everybody experiences this force right here, and all's well and good, right? Well, what happens when we, and remember this is energy through a loop, like a loop-de-loop on the roller coaster, right? Which I love. Roller coasters that do that's awesome. Right? What happens when I turn this thing like a loop-de-loop, turn it on edge? Now, what messes with our whole centripetal force? Gravity. Now we got gravity and centripetal force going on, right? So I'm going to tell you, we don't really care about those. We're going to ignore those. So let's look at the top and bottom. I want to look at here versus here, and let's not think about all the equations and crap on there yet. But so now we're standing like that guy enjoying his ride on the Gravitron, right? There's you, Arnold, right there, right? We turn him on edge. What happens? What does he feel? What's the difference between here and there?
He feels gravity.
Okay, he feels gravity. Cool. How?
On the top, he feels more force. On the bottom,
On the top, he feels more. On the bottom, he feels less. What you saying? So you're standing there cruising around in your circle, feeling great, and then they tip you on edge. You feel more force here,
Not lighter.
right? So here, gravity's pulling you away from where you're standing, right? Here's you standing, right? Gravity's pulling you away. Down here, gravity's pulling you towards, right? So, and one little thing, little paradigm shift I'm going to make now. When I'm standing here on the ground, what do I feel? Do I feel my weight? No, what I feel is the ground supporting me, right? I feel the ground holding me up. What I actually feel is my normal force, right? And so at the top, my normal force is centripetal force. Oops. Minus my weight, because the weight's pulling me away from the ground, right? The ground as I feel it. How about down here? Normal force equals mv squared over r plus the weight, because the weight's pulling me the same direction as what I'm feeling, right? Does that make sense? So at the top, I feel gravity opposing my centripetal force. At the bottom, I feel gravity and the centripetal force working together. So I feel heavier at the bottom, lighter at the top, right? Are we cool with that? Okay. So I'm going to move forward here. There's a lot of writing on this page, but there's only a little bit that I want you to worry about. Okay, and I'm going to pause. The part that's circled in blue is what I'm worried about. When normal force equals 0, that means I'm no longer touching the floor, right? If I'm upside down in a loop, not good, is it? Okay, so when the normal force equals 0, that's when I fall, when I'm upside down. Okay, I'm going to pause this in case anybody wants to write this down in the classroom. All right, I want to move. Here we go. So I want to ask you something here. A little math magic. When they equal 0, what does that tell me about those two terms?
Cancel out.
They cancel out, right? They're equal to each other. This term equals this term, right? So when I no longer touch, I know that my right? And actually, yeah, we'll get there. Right? Math, this is not the new MathWise, right? I hope. Some of you look a little shell-shocked yet, right? Masses will cancel. If I'm gonna solve for V here, and I'll explain to you why in a second. Right? I just took this equation and solved for V. Don't worry about, I'm going to explain why in a second, but everybody follows the math, right? Well, what if I do this, right? That's the velocity necessary to traverse a loop, right? The velocity has to be greater than or equal to the square root of GR, right? What we just kind of explained here. In order for me to make it through a loop, for this to be bigger than 0, right? The velocity has to be greater than or equal to the square root of GR.
0.
It's going to be 0. That's where you just lose contact, right?
Yeah.
So you can even say greater if you want, whatever. Yeah. Okay? But this would be the velocity at which you lose contact, right? So based on what we just explained, when the normal force reaches 0, that's when you fall, right? Which means these two are equal to each other, right? So if I solve that, this is the velocity at which